We've had exponential equations before, but we've had type 1, which were the ones where you could rewrite one side or both sides so they have the same base, and then you can set the exponents equal to each other. But what if you can't do that? Or what if it's really a long, drawn out process where that's probably not the best thing to do? Then that's a type 2 equation, and that's what the first half of this section's about. So the thing that you end up using a lot, it's these first two bullet points, where if two quantities are equal, then the logs of those quantities are going to be equal. And you can use any base you want, like it says up there. You're probably going to want base e or base 10 because those are on your calculator, and that way you can get a decimal approximation. But you could use other bases if you really wanted to. And why do you need to use this? Like, why do you need to take the log of both sides? Because usually what you have to do, like it says right here, usually you have to get the variable out of the exponent. So usually the thing that you're solving for, it's up in the exponent, you need to get it out. And that's how you do it. If you take the log of both sides and you can bring the power out front, that's how you get the variable out of the exponent. And you'll see it over and over again in these examples here. The book usually uses a base 10 log. I usually use a natural log. It doesn't really make a difference. They would both give you the same answer. Like for number 1, you can see its answer right here. Base 10 log of 13 over base 10 log of 5 is the exact same number as this. So anything would work, if you want to use base 10 log or base e natural log. I guess if in your equation, if you have a base of 10 in it or a base of e in it, then maybe one is slightly faster than the other, but generally it doesn't matter. So, all right, this first one, this is what I'm talking about. We've got the x up there in the exponent. You need to get it out, right? Because ultimately you want x equals some number. So if you take the natural log of both sides, then there's that rule about if you take the log of an exponential expression where you can bring the exponent out front, which is what happens down here, right? I brought that x out of the exponent out front, but then you can solve for x, right? Because this is just multiplied by some number, right? Natural log of 5 is just some number. Natural log of 13 is just some number as well, so you could just divide both sides by the natural log of 5, and then you're done, right? So natural log of 13 divided by natural log of 5, whatever that is, that's x. Similar thing over here. The base is a fraction, but don't let that throw you off. You basically do the exact same thing. It's the x is in the exponent, you got to get it out. So natural log of both sides, bring that exponent out front, and then divide both sides by the natural log of 1/3, which if you want to write it without the natural log of a fraction, you can, because the natural log of 1/3, using that quotient rule from a previous section, would be the natural log of 1 minus the natural log of 3, but the natural log of 1 is 0. So it ends up being the negation of the natural log of 3. So you can write it either way. I guess if the next step was to put it into the calculator, it probably doesn't make too much of a difference, but you could write it either way. There is an alternate way of doing this, which would be to say that you could write 1/3 not using fraction notation. You could say, well, that's 1/3 to the first power. So you could write that then as 3 to the negative 1. So 3 to the negative 1, then to the power of x. You could multiply the exponents together, and you have 3 to the negative x. Again, you would take the natural log of both sides to get that negative x out front, but then you divide both sides by the negation of the natural log of 3. You end up there, which was the same place we ended up over here. The other two examples that are on this page, this one's got a base 10, and then number 4's got a base e. So I think there you could argue that maybe with number 3 you're better off with a base 10 log because there is 10 as a base in this expression on the left side. And then here number 4 you could argue that natural log might be a little bit better because you've got a base e on the left side. But if you used a natural log on number 3 and used a base 10 log on number 4, you would get the right answer. It would just be like one extra step. So whatever you're comfortable with, I suppose. But that's why I used a base 10 log here, even though I usually don't. It's just because of that base 10 right there. Because then if you take the log, the base 10 log of both sides, you can bring both exponents out front, which is what happens down here. But then on the left side, you have x minus 3 times the log of 10. But the log of 10 is 1. Because then what the log of 10 would be, it's the number that you would have to raise 10 to in order to get 10. You go, well, 10 to the first power is 10, so it's 1. Yeah, this is 1. And that's why it's not here in this line down here. Because really, this is x minus 3 times 1, so it's just x minus 3. And then if you're solving for x, Then I guess get everything with an x in it on one side and get the constant on the other. So I did two things to get from this line to the next line. I subtracted x log 5 from both sides and added 3 to both sides. But then once you're here, you could factor an x out of this, which is what I did right there. And then this thing in parentheses is just some number, so you can divide both sides by that, and then you've got it solved for x. Number 4, similar kind of idea except with a base e, so natural log I think fits in a little bit better there. Bring down both of the exponents, bring them out front, and you have the same thing here. So the natural log of e, that's like the base 10 log of 10. Natural log has a base e. So the natural log of e is a number that you would raise e to in order to get e. So it's 1. So if that's a 1, then this is 0.5x times 1, so it's just 0.5x. And then same thing as in number 3, get everything with an x in it on one side and then constant on the other side, factor an x out, and then divide by this number that's in parentheses, and then you've got it solved for x. Number 5 is really short because it doesn't work. And you might be able to see it just from here where you'd say, wait, any power that you raise 11 to, you'd have to get a positive. There's no way you're getting a negative 8 out of this. If you can see it right away, that's fantastic. But even if you start going, if you don't see it right away, that's okay, because then you think, well, I got to get that x out of the exponent, so if I take the natural log of both sides, I'd get on the left side natural log of 11 to the x. Okay, that looks fine. Then you'd bring the x down. But then on the right side, the natural log of negative 8, that doesn't work, right? You can't take the natural log of a number that isn't positive, and I mean for any base, right? Natural log, base 10 log, base 2 log, any of them. So the thing that's on the right is undefined, so there's no way to solve this, right? Because you have natural log of 11 to the power of x equals undefined, so that doesn't really work. That doesn't go anywhere. So there's no solution this time. So once in a while that is going to happen. So nice and short at least, I suppose. Number 6, that does not happen. Number 6, you do get an answer, and there's actually a lot to do with number 6. So the first thing I would think is you want to do that move that we've been doing, where you want to take the natural log or the base 10 log of both sides to get the x out of that power. In order to do that, you want that expression on the left to just be an exponential expression. So no plus 1, no coefficient out front, so we got to get rid of them. So the first thing I did was I said, well, if I subtract 1 from both sides, that'll fix this problem. So, right, that's what you get when you subtract 1 from both sides. Then I don't want this coefficient of 5 here either. So if you divide both sides by 5, you end up here. And now you got the thing that you want. Because here, if you take the natural log of both sides, you can bring that power out front. So here it is. I took the natural log of both sides, brought the 3x minus 2 out front, and then let's see, then I just divided by the natural log of 1.2. I guess you could distribute this first if you wanted to. It doesn't make too much of a difference. But you end up here, then getting the x term by itself, so adding 2 to both sides, you end up there. And then dividing both sides by 3 to get x by itself, you end up there. Then there's number 7. Number 7, I think, is easier than number 6. It just has a lot of logs in the final answer. Right? A lot of them. Got 4 of them in there. So we have the same issue that we've had before where you've got x's in the exponents. You want to get them out. Okay, we take the natural log of both sides and we can bring the powers out front. So x minus 4 times natural log of 3 equals 2x plus 5 times the natural log of 7. Distribute both of these because on either side of the equation, you're going to have a term with an x in it and you're going to have a constant. So there's the natural logs distributed on both sides. Then get everything with an x in it on one side and both constants on the other. So I guess it's 2 steps to get from this line to this line down here, right? Subtracting 2x ln 7 on both sides and adding 4 ln 3. Then from there you can factor an x out on the left, and then you can divide both sides by what's in parentheses to get x by itself, since ultimately this thing is just some number. So you end up here. So that's kind of crazy looking just because there's so many logs in there. But I actually think 7 is easier than 6. At least it feels easier to me. Maybe that's just my perception, but that's the way that I look at it. The other half of this section is about log equations. And basically the biggest step I think here is to switch it. Just switch it into exponential form out of log form. Because in log form, it's a lot harder to process, it's a lot harder to interpret. So I think that's the best move. So the first thing is you want to get a single log, which I guess here, like in number 8, and you can see it down here, I've got that 3 in the front, and I put that back up into the exponent. Because then that's when you can do a direct conversion from log form into exponential form. So you just want a single log, no coefficient out front. You don't want 2 logs added together, because like if you had that, then you could write that as the log of a product and turn that back into a single log. That kind of stuff you might have to do. But then once you've got it written this way, then you can convert to exponential form, where then it's the same base, and then it's, that base raised to whatever's on the other side of the equation equals the thing you're taking the log of. And then usually that's a lot easier to handle. Another way to do it is, and this is basically using the idea that the log and exponential functions are inverses of each other if you use the same base. So like how here where it says if b equals c, then a raised to the power of b equals a raised to the power of c. So that's like if you had some log here, so log base a of r equals s, then if you use the same base, then a raised to the power of the log base a of r is equal to a to the s. But then this thing that's on the left side is actually just r, because log with the base a and a being raised to the power, those functions are inverses of each other. So that just ends up being r. So that's the other way that you can look at it. The first option I think is what most people end up picking, but the first two, I did them both ways. So it's option 1 on the left, option 2 on the right in both cases here. So with number 8, I guess either way, like whichever option you're going to pick, you want to get it to where the left side is just log of something without that 3 out front. So usually, at least in the first half of this section, whenever we use this exponent rule, we've been doing it the other way, like you bring the exponent out front. But here, we're actually going to take that 3 and put it back in the exponent, so that way it's just a log with a coefficient of 1. So 3 log x would be the same thing as log of x cubed. It's just using that exponent rule in the opposite direction. But then if you use the definition of log, you go, well, this is base 10 log, so 10 squared would be x cubed, and that's right here. So then 100 is x cubed, which would mean that x would be the cube root of 100. The other way of doing it is you can say, well, if these are equal, and this is a base 10 log, 10 raised to the power of the thing that's on the left side up here would be equal to 10 squared. But then 10 being raised to the power and then base 10 log, those are inverses of each other, so that left side is really just x cubed. So an x cubed is equal to 10 squared, so x cubed is 100. So take the cube root of both sides, x is the cube root of 100. So you get the same answer either way. Same thing with number 9. So number 9 is already ready to go as far as you just have the log of something, right? You don't have like a coefficient out here that you got to deal with. So if you just use the definition of converting from log to an exponential equation, this has a base of e. So it would be e to the 5th is equal to 2x, and then to get x by itself, you just divide both sides by 2. All right. The other way of doing it is, since it says base e, you'd want to use the base e if you were going to use exponentiation. So e raised to the power of ln of 2x equals e to the 5th. But then on the left side, e being raised to the power and natural log, those are inverses of each other, so that's really just 2x. So 2x equals e to the 5th, divide both sides by 2, you get the same answer as you got over here. Then number 10 and number 11, the other two that are on this page, these I just did with option 1 because I think that's the one that for most people feels, I guess, more straightforward. But here we've got a base 9. So then if you're going to convert this into exponential form, you'd say 9 raised to the power of 2 equals the thing that's in the parentheses, 7 minus 2x. So that's what I've got right here. But then 9 squared is 81. But then this is just a linear equation to solve, right? Subtract 7 from both sides, you end up here. Then you divide both sides by -2, you end up there. And you get that x is -37. Number 11 has got 2 logs, but they're added together. So using another one of those log properties and using it in the reverse order from how we typically use it, you can rewrite the sum of 2 logs as the log of a product. so the log of x times x squared. But x times x squared is x cubed. And this is base 10 log since the base isn't written in. So 10 to the third power would have to be equal to x cubed. But then if 10 cubed equals x cubed, 10 would have to be equal to x. I guess technically you take the cube root of both sides, but I think you can see it right there that that would have to be the case, that 10 and x would have to be the same. The examples on the fourth page, they're not all that different. They tend to have multiple logs in them, but they also have a new wrinkle, which is that you can have extraneous solutions. So with number 12, you've got the sum of two logs. So you want to rewrite that as a single log, so you can write as the log of the product. And x times 3x minus 13 is going to be that, 3x squared minus 13x. And so then if you use the log definition to switch it into an exponential equation, you have 10 to the first power equals the thing that's in parentheses, the 3x squared minus 13x. But then subtracting 10 from both sides, you end up here. This factors. Then you can use the zero product property, and eventually you would get that x is equal to negative 2/3 and x is equal to 5. However, some of these logs aren't defined, right? Like if you sub in a 5, everything's okay because you say, okay, log of 5, that's fine. And then 3 times 5 minus 13, that's 2. Okay, you can take the log of that. But with negative 2/3, it doesn't work. The log of negative 2/3 is undefined, right? So that's why this fails. Really, you just need one of them to fail. But here, actually, they both do. I wrote it in number 13 that they both do. But here they also both do, because if you sub a negative 2/3 in here, you get negative 15. And you can't take the log of negative 15 either, right? You can't take the log of any negative number. So that's what makes the negative 2/3 extraneous. It's that you can't take the log of a number that's not positive. So basically then when you get multiple answers like this, you have to go through and check them, kinda. You don't have to check them all the way. You just have to check the logs, like back in the original equation, to look at those logs and just to make sure that they're both defined, right? So they both got to be defined. If one of them fails, then that's it. You've got an extraneous solution. Even though in this case for negative 2/3, they both do. And the same kind of thing happens with 13, right? Here you'd say, okay, it's the sum of two logs. You can make that the log of a product. But then since this is base 2, 2 to the third is x squared plus 7x. Get everything on one side and a 0 on the other. You can factor. And then zero product property. Your two answers would be 1 and negative 8. And 1 is okay, because then you'd be taking the log of 8 and the log of 1. That's fine. Those are both defined expressions, right? But then with a negative 8, you'd have the log of negative 1 and you have the log of negative 8. Those are undefined, right? You can't take the log of a negative number, so that makes x equals negative 8 an extraneous solution, right? You get those undefined logs up there when you sub in a negative 8 for x. Then down here, 14, there are a bunch of different ways that you can solve this one, but I figured this was probably the shortest and hopefully the most straightforward. You could combine all three of these into one single log. That's the main other way of doing it, and there are a couple of different ways to do that, to go about doing that. But what I did was I combined the first two, the ones that had x's in them, and I said, okay, well then that's the difference of two logs, so that's the log of a quotient. And then this minus ln3, I just said, well, if I put that on the other side, then really we end up with that 5 plus 4x over 3 plus x equals 3. You could argue that you could jump right from this to this because the natural log is a one-to-one function, and that's true. But just to keep things rigorous, I have this intermediate step where I just said, well, if these are equal, and then if you raise e to this power and e to this power, and I'm using a base e because I've got natural logs, right? So I'm keeping the same base. Then e to the natural log of that expression, of that quotient, is just that quotient. Then e to the natural log of 3 is just 3. But then this is solvable, right? Because then you can multiply both sides by 3 plus x. You can clear fractions. Then if you solve for x, eventually you end up with 4. And that's not going to cause any trouble, right? That won't be an extraneous solution. It's all pluses in here, and the thing that we got as a solution was 4. That's a positive number. So there's no way that you'd get negatives in here, but you can check them, right? If you put a 4 in there, you get 13. Okay, that's fine. You can take the natural log of 13. You put a 4 in here, you get 7. That's fine. You can take the natural log of 7. So we're okay there. Number 15, once again, we've got the sum of logs over here, so we can rewrite that as the log of a product. And then here, I just went ahead and did it. Instead of saying 2 to this power equals 2 to that power, which you can write it in, it would be the equivalent of this step right here, right? Just with the other base, since here these logs are base 2. But you can also say, well, log is a 1-to-1 function. So if these two logs were equal, then 2x squared plus 4x would have to be equal to 16. Then I got a 0 on one side, and then everything here is even, so you could divide both sides by 2 to make the number smaller, which is basically what I did. So then with x squared plus 2x minus 8 equals 0, that does factor to x plus 4 times x minus 2. 0 product property. 2 ends up being okay, because if you sub that in up here, this is the log of 4. This is also the log of 4. Okay, log of 4 is a defined thing. You can take the log of a positive number. But negative 4 causes trouble, right? Because here you'd have the log of negative 8. Here you'd have the log of negative 2. So that's an extraneous solution. I just put, because the log of negative 8 is undefined, it's either or, right? The log of negative 8 is undefined. The log of negative 2 is also undefined. Either one of those by themselves would be enough to make that fail, essentially, into where that would be an extraneous solution.